Hello and welcome back to Calculus 1. This is the last section in chapter 3, 311, related rates. So it's applied section, which means all of our problems are word problems. And it's one of my favorite sections because we get to compute things with this and make our lives better, whether it's job or stuff that we calculate for ourselves. I'm going to start with first dissecting the title. Related rates. This means that there are multiple rates, at least two, right? And they will be related through some kind of a formula. So, related rates. The word rates means derivatives, and related means some kind of formula, right, that acts upon these derivatives, and then the rates are related through that formula. So let's think about first the related concepts that we might explore and think about. So, behold a cube. This is just an ice cube. This is an ice cube that exists. You can hold the ice cube in your hand. That ice cube has all sides to be the same, hence cube, because we also have rectangular prism, which would not be a cube, which has different sides, right? But if all the three sides are the same, it's called a cube. It's still a rectangular prism. It's just a special case called the cube. Now, what is the volume of this cube? Yes, a cubed. So volume is a cubed. Now, what is volume connected to? Well, it's connected to the physical existence, right? Some of us have a bigger presence in this planet than others, right? Just by looking at the volume. That makes sense, right? Yeah. Volume-wise, I take much more space than you. That's maybe double. All right? So. Yeah, I love it. Every time. Just want to see who catches on. So, we have the volume, which means that we can hold that object in our hand. Now, what happens as you hold ice cube? It melts, right? Does it instantaneously melts and it's gone? No, it takes time. So if I want to observe change in volume over time, I better take the derivative in time. So our derivatives in this section are going to be taken in respect to time, because I want to measure the change in time. So now I can use implicit differentiation and come up with the formula. So derivative of a v is 1, and then follow with the chain dv dt, because we were taking the derivative of v in respect to t. And then on the other side, I have 3a squared, that's the derivative, and again dA dt as a chain. So now this formula here is called related rates. Related rates formula, because it relates two rates. There is a dv dt, rate of change of volume in time, and dA dt, rate of change of the length of the side in time. So we have two rates in this particular problem, and they are related by this other part of the formula, so times 3a squared. So now what can I do with this? Well, I can learn, measure, calculate how fast is this melting. Or I can also measure how fast it's shrinking because the sides are getting smaller. This concept should be familiar to all of you because at one point in life you notice that the ice cube that you have in your drink or on a desk or somewhere is getting smaller, right? If you haven't, you still have a chance to run that experiment, right? It's only April, so probably snow till June, and then we'll go into monsoon season after that for 2018. So what do we have with this problem? What can I measure? I can easily measure the change of volume by either water displacement or, whatever. But I could also observe the change of length of the side because I can have the ice cube next to a ruler, right? And then say that we are losing so-and-so, fractions of an inch per minute or per hour or whatever, right? So something I can measure in this formula and other things I can compute. So all you need to do is to plug these numbers in. So let's say that the problem says that ice cube is melting at the rate of 0.3 cubic inches per minute. Find the rate of change of the side when side is 4 inches long. So this would be the problem. Now we already know that dV dt is equal to 3a squared dA dt. As you are reading the problem, you can quickly pick up from here your dV dt. Now, how do I know that dV dt is equal to negative 0.3? Well, I have two clues that tell me that this has to be dV dt. And I have to invoke common sense. So if it's not common sense, try to get to the point where it is going to be common sense. First of all, the word melting. You are losing volume. All right? That's what melting is. So if ice cube is melting, it's losing water, it's getting smaller, therefore it's losing volume. So losing negative, right? Numbers are getting, the ice cube is getting smaller, so negative 0.3. So that would be the first clue that it's dV dt. What's the second clue? Units. Inches cubed, that's a unit for volume, and minutes, that's the unit for time. If you're masters of these units, you know what you do with general chemistry? It's a joke. Because they give you, in that class, right, in the text, they give you units with numbers. As soon as they give you units, you should be able to write the formula, right? What's the speed measured in? What's the speed measured in? As you drive, what is speed measured in? Miles per hour. What's the formula for speed? Distance over time. Wow, what a concept, right? That's what it takes. You look at the units, and then you just put those physical concepts in their place. So if the speed is measured in miles per hour, then your formula for speed is distance divided by time, because distance is measured in miles and time is measured in hours. Very simple. All of the mathematics and physics and chemistry works that way, right, by the way, with those formulas. So dimensional analysis will help you a great deal to figure out what type of information is given to you. So again, in this particular problem, the way the wording is there, you have two clues that this is dV/dt. The word melting means losing the volume, and also inches cubed, that's volume. Volume divided by time. There's your volume divided by time in the derivative. Negative, because we are losing the volume in there as this thing is melting. Great. And it's clearly stated over here that the length of the side is 4 inches. Now you have to be careful with units, right? If one is given in feet, the other one's given in inches, you have to convert, right? So now plug everything in. You have your negative 0.3 is equal to 3 times 4 squared, and you do not have anything for dA/dt, but that's good. That's what you're looking for. It says find the rate of change of a side. Look. See this peanut? That peanut is ddt. That's rate of change of what? A side. So that's the way you understand these things. You separate that one variable that it's in the numerator, and the rest is rate of change of whatever that thing is. Rate of change of area, rate of change of volume, rate of change of diagonal, rate of change of side, whatever it follows there. So now, what do I have? I have that dA/dt is equal to negative 0.3 divided by 3 times 16. These guys cancel. We get negative 0.1 divided by 16. And what do we get? .1 divided by 16?
Negative 0.00625.
Negative 0.00?
625.
625. All right, great, thank you. Units, a point on your exam. Well, a side is length, so it's a single inch divided by the same measure of time, which was minutes. So if your volume, if you're losing inches cubed per minute, then the side will be losing inches per minute, which makes sense. Let's jump into an environmental problem, right? Oil rig spills the oil. We need to do some cleanup, right? Sponsored by BP. What can I do? I don't have stocks there. Anyway, so what's happening? If there's the oil spill, it generally creates the surface, right on the surface, around the oil rig, which is in the center. And then it expands in all directions. So the circle will be getting larger and larger and larger as the time goes on. So the longer you wait, the more cleanup you have to do. So now we are trying to understand what are we doing, right? We are cleaning the surface, which means that we are cleaning the area of this circle. This circle is going to have a radius r, and that radius changes in time. The longer you wait, the more oil is coming out of the whatever broke, and then this circle grows. If the radius grows and the circle grows, what else grows? Area that we need to clean up. So now I will start with the area pi r squared. This is the formula for area of the circle. And then I am going to hit that formula with the time derivative, because I want to study and understand how this thing evolves in time. So now what I get is the dA dt is 2 pi r dr dt. And there is my related rates. Related rates formula. This related rates formula relates what? Change of area in time and change of radius in time. So these are the two: change of area in time and change of radius in time. So now it says in the problem that the radius of the oil patch increases at the rate of 30 meters per hour. 30 meters per hour. It says the radius of the oil patch increases. So what is the variable over here? What do I get to put? dr over dt. Very good. dr over dt. Radius is length. It's a one-dimensional length. Therefore, because meters are given, right? So that's 30 meters per hour. They want to calculate the change of area. So that's the unknown, where radius is 100 meters. We get to plug this in. dA dt is the unknown. Great. On the other side I have 2 pi r is 100 and the dt is 30. So what is this? This is 6,000 pi meters squared per hour. That's about 18, right? More than, because pi is 3.14, so think about like 20,000 meters squared. And that's the growth. It's a lot. This is about 20,000 meters squared per hour. What's the, in square meters, what's the area of this classroom? Well, let's talk feet then. What are the measurements of this classroom in feet? Exactly. Give me exactly. I don't want the approximations. You can tell me exactly. Anyone, please? There we go. Some of you got it. Nice. Exactly, I want. I see you counting. Good. What are you counting? Yeah, the ceiling tiles. Look at that. That's 2 by 4 each one. 2 feet by 4 feet. Calculate across, calculate down there. I want exactly in feet. How many? Calculate the number of this one, this way, times 2. Number that way, times 4. Right? I mean, what do you do when you go to the doctor's office? And you sit there? You immediately get all of the specs of the waiting room, right? You get the surface area of the floor, so how much is the new carpet, how much to paint the whole place, huh? You don't know what can come up, huh? Strike up conversation with someone. Do you know that the surface area of the carpet is? Yeah, and at today's prices, you can look it up. You said you like to play on the phone, right? Say I can carpet this and undercut the empire, right? Yeah. Calculate right there on the spot. Useful stuff. So what did you come up with the classroom? What do we have one way? 17 this way? Times 2, so 34 feet. Okay. And how about that way? 7 times 4? Thank you. Oh my God. So that's the classroom. Now in feet, 3 feet is about a meter. So divide by 3, right? So you get about 11 meters by 28 divided by 3 is like almost 29. Like 27, that's a 9. So about 9 meters. So this is like a 99. So this is about 100 meters square. So look at this classroom. It's about 100 square meters. Now look at the number out there. 20,000 per hour to clean. How long would it take to clean this much oil spill? To scoop it up with a special vacuum, right? And then 200 times more. It's 200 of these classrooms. And that's added in the hour. Now remember, after an hour, when you add that many, well, the radius grew as well. So in the next hour, there will be much more added. Because the bigger radius, right? And now this number stays the same, but this number grows. So then this number has to grow in the next hour. Which is why you don't want to sit. If there is an oil spill or something, clean it up right away. It's going to get worse. It's going to get worse. Good. Most of the problems that we are dealing with in this section are based on geometry. And that will require you to know area formulas, volume formulas, perimeter formulas, and all of those good things. Now we're going to categorize those, so we'll be fine. The other big part that I'm talking about is this fact that you can read units and then know which concept is given to you. So let's take a look. So we've seen the volume of the melting cube. We've seen the surface area. Now let's think about distance of 2 airplanes approaching the airport. So we have the airport right here, and we have one airplane coming in this way, one airplane coming out this way, and clearly there is the distance in between them. This one is going X direction, this one is going in Y direction, right, as they are approaching the airport. Is it important to know the distance and separation between these two planes? Yeah, we want to keep them apart, right? That would be good. So, how do we do that? What kind of geometry is presented there? And then what type of a formula should we use to deal with this? Very good. We see a triangle. Now, what type of a triangle? The right triangle. What kind of formulas do we have for right triangle? So here, I'll write in green. So we see a right triangle. I want to write all of the formulas that pertain to right triangle. Forget about the picture, forget about the problem and everything. Let's just talk. What are the formulas we know about the right triangle? What? Pythagorean theorem. Okay. What else? What else do we know for the right triangle? We don't need that. That's the Pythagorean theorem. A squared plus b squared equals c squared. What else? Just triangle in general, guys. What formulas do you have for triangles? Yes. What is that? Thank you. Area formula. We know area, 1/2 base times height. What else do we know? Again, don't think about the problem. Think about just general triangles in general. What else do we know? If you have area, what's the other one? Well, no, this is a 2D object, so no volume. Parameter. So what's the parameter? A plus B plus C. Thank you. What else do we know? What other formulas do we know? Whole bunch of them. If you have a right triangle, you can do trig. Yes. So we have sine theta, cosine theta, tangent theta, dot, dot, dot. So these are the formulas that you have, related to a triangle. Now you go and you look at your situation. Are we talking about area in any of this? What do we want? We want to see how fast the distance is changing between these. So do we need area as the concept? No. How about perimeter? Right? So that could be something. All right, fine. How about any of the trig? No. Why? Do we care about any angles? Right? The trig has to have this angle theta. So we can kick those out. Pythagorean theorem? Yeah, we have to keep that one in loop as well. Now we're talking about the distance d. Now, do you see that the perimeter would actually not work in this case because x, y, and d will all change at the same time? We don't have that many variables, right? We just reduced it down to Pythagorean theorem. Great. Let's write Pythagorean theorem for this triangle. X squared plus y squared is equal to capital D squared. That's the Pythagorean theorem, and then I am going to hit this with a time derivative to get related rates. The derivative of x squared in terms of time is 2x dx dt plus 2y dy dt is equal to 2d dd dt. Now it's dd dt that we are looking for, right? Because we are looking for the change of the distance in time. This is what we are after. So change of distance in time. That's what we're after. I hope you see that these 2's drop everywhere. If you divide both sides by 2, all of the 2's are gone. Now let's dissect this formula. I'll write the formula one more time so we have it clean. X times dx dt plus y times dy dt equals d dd dt. There we go. Good. I want to know what these things are. This is applied problem. Every single variable has to mean something. Great. Talk to me. What's x? What's x?
It's the rate of that plane on the top.
Not the rate. It's the distance. X is the physical distance of the plane, the first plane, right? So that's the distance in x direction. Now, what's dx dt? Okay, so what is the derivative? Yeah, so what is that? I'm talking about physical constants now. What is that in our physical reality? What's dx dt? Yes, there we go. That's the speed of that airplane. So dx dt is the speed of the x airplane. What's y? Distance in y direction. And what's dy dt? Speed of the y airplane. Nice. And what's d? Capital D. What's capital D? Distance between two planes. And what's dd dt? Well, we know it's a change of that distance, right? So there you go. Every single variable must have physical meaning, otherwise the formula that you have is garbage. It's as simple as that. So you have to be able to identify every single piece of your related rate formula, and it has to do, something has to have, right? Great.
What's the
dt? It's the change of distance in time between the planes. As both planes are coming towards the airport, the distance between the planes is getting smaller. My question too is, who's computing this? There's JFK, there's Newark, there's LaGuardia, and then there's all these small airports around. Who's computing that?
Calc1 students.
Calc1 students? Oh, bad time to leave now. So some Calc1 students. Oh, we do? And this is when it's not busy. relative distances between each and single one of these. Vertical, horizontal. There's the stuff. Right? So you definitely don't have people sitting computing that stuff. Your job is to write the software that is going to make sense out of this. Right? That's where the jobs are. So figuring out the equations, putting those in a code, and then feeding what is necessary. Each airplane is sending in my distance from blah, blah, blah. My speed is blah, blah, blah. The software keeps computing things. And we have, this is live, by the way. So you can pick this guy, right? And you have all of the information about it. And then also some other cool features like this. I know. Right? So this is what you do. Now look at that. Ground speed and right. You can buy up the account for this thing and tell. So get more details, obviously. Every single one. It doesn't matter where it is in the world, right? You get to track that. And then you get to compute things. The problem we have at our hands? 2 airplanes approaching, and we want to know their distances. There are more variables than just the distance and the speed. We got to worry about the amount of fuel and all other things that are important, right? Connecting flights for, to have enough time for baggage transfer and everything else. So it's not just, who gets there first lands. So there are, a lot of different things to worry about. So now, clearly, if I have 2 planes approaching like this, one plane says I am 10 miles away, the other one says I'm 13 miles away, the one is going 500 miles per hour, the other one is going 470 miles per hour, you just plug those numbers. That's not a problem. The biggest issue of this section is you understanding what these things mean and how they're connected to the physical reality. That is the part. And that's where your physics and your engineering gets born. Because you have to be able to connect the physical reality. And this is the stuff that I did with these arrows, right? X is the distance, which is the location of the airplane 1. DHDT, great. X distance over T, time, distance over time. That's the speed of the X airplane. Same thing for Y. And then you have DHDT, which is the distance and separation between 2 planes. Now let's take a look at... Now, clearly, when they give you speeds and stuff, you just plug them in. If you understand what each one of these means. Let's launch a rocket, Falcon 9, right? And design a camera that will have the rocket in the center of the shot at all times. There's a lot of old footage, with Joe standing somewhere on the side, shaking, right, to get the shot, and it's like rocket is all over the place, right? You can design a nice mechanical thing with a servo motor, right, that will start at 90 degrees looking at a rocket, and then as the rocket goes up, will slowly go up, right? Well, this motion right here is going to be controlled by a motor. Motor should be controlled by the controller. Controller is controlled by your programming. And what's in the programming? It's the formula that we have to develop so that the code gets the input on the speed of the rocket, and then right? That all with related rates tells you the rate of this swivel. And this over here is the simply angular velocity. You have the velocity on the straight, like the linear velocity, and then you have the angular velocity, which we call omega in physics. So let's design the system. Here's the ground. Here's the little bunker where we are going to have our camera. That's the high definition, high-tech camera. Automated and everything. Here's the rocket. Looks like a missile, but it's a rocket, okay? So Falcon 9. There you go. It says SpaceX on it. And now we're going to shoot this rocket upward, right, to go. It's going to be covering height, and the camera is going to record horizontally first while this thing is still on the launch pad, and then it's going to swing this way, right, to catch the rocket up there. This distance, I generally, when I teach this example, I use 500 feet, but you can put whatever number, whatever is the safe distance so that the flames do not melt the camera, or the exhaust gases and things do not create a cloud so camera can't record anything. So, you know, you figure out, right, how far out camera should be. Technically, don't put the camera where you wouldn't be standing to hold the camera. Put it that way. Too bad that the experiment has only one trial. So, all right. Exactly. So, what is important here? Well, clearly, this angle theta is important because it is at the angle that it's going to rotate. So, angle is important. And now I have a right triangle and I have the angle. So, Pythagorean theorem? No. No angles in Pythagorean theorem. Good. Area? No. Perimeter? No. Trig? Yes. Right? Now, which trig? I have 6 of them.
Sine.
Why sine? What's the sign?
Height.
It's the height, okay.
The line. The
Why 10?
the-
Ah. So if this is my angle over here, we have opposite and we have adjacent, and that's tangent. So good. So let's write my tangent function here. Tangent theta is equal to opposite, which is the height, divided by 500, which is the adjacent. From where I can write that the height is equal to 500 tangent theta. I got the formula. Let's develop this formula in time now. So hit it with the derivative. In time. There's the derivative in time. On the left-hand side, we have DHDT. On the right-hand side, we have a 500. What's the derivative of tangent? Thank you very much. D theta dt. What's DHDT in this formula? What's DHDT? Which is what? Speed of the rocket. There we go. Thank you. So this thing is speed of the rocket. Do we have that? Yeah, we do, right? That's something that we can measure. Now, what's this one? D theta dt. What is that? Yeah, what is that?
How much the angle changes over time?
Uh-huh. How much the angle changes over time. Guys, look at this. You see this? This is the camera lens right here, right? Look at that. As the time passes, you see that the angle at which the camera is looking. Imagine the rocket right there, right? And as the rocket goes up, this better go up. And it does, right? So it's recording, and the shot is always centered. This one over here is the omega, angular velocity. That's what we are looking for. That's the speed of the rotation of the camera. That is what the motor needs to turn. When the motor spins, that's what's given. Number of revolutions per minute, right? The theta, 360 degrees, one revolution, right? So you say 3,000 RPMs, it turns 3,000 times a minute. That's what it means, right? 3,000 RPMs means it spins 3,000 times in 1 minute. That means it goes 360 degrees, 3,000 times in 1 minute. That's what 3,000 RPM means. So this is omega, angular velocity. If you want to ask a physicist, but if you're asking an engineer, engineer will tell you change of angle in time, because that's exactly what's happening on a camera. Angle is 0, angle is 15 degrees, angle is 30 degrees, angle is 45 degrees, angle is 60 degrees, angle is 90 degrees, right? It's a change of angle in time. So I'm going to use engineering language, change of angle in time. Great. So I have the formula here. I need to solve for that because that's what I'm looking for. I need to program that in. Right, so I have to solve for d theta dt. That's what I'm looking for. What I get on the other end is DHDT divided by 500 secant squared theta. Now some basic algebra will tell us that 1 over 500 DHDT times cosine squared of the angle. See you next week. So we have our d theta dt is equal to 1 over 500 cosine squared theta DHDT. And this is the related rates formula. What are the rates that are related? The change of the angle in time with the speed of the rocket in time. So now you tell me that the rocket is going so and so miles per hour or kilometers per hour, which if you watch the Falcon, let's go. I don't know, hopefully. Oh, I didn't go through.
Do they have any images on there of the Chinese space station?
Mm-mm. YouTube shooting today. At least 4 wounded at some... Huh? Are these are real news. CBS, CNN. Yeah. There's a shooting in YouTube right now? Well, that's not good. Well, no, shooting is good. Okay, Falcon Heavy launch, I think that's the one that we... There we go. I played this video in class already, but you see it. There we go. There's the speed, right? And as that updates, right, the software needs to feed that quickly into the formula. The formula grinds up on how much, right, it needs to change the angle so that there is a shot. And obviously, you know, you have to program the zoom and all of these kind of things, but at least you have the right idea on, you know, where to start. So that's as you can see, all of this stuff applied. We did oil spill, that's environmental stuff. You did ice cube melting, that's the drinking. We did the airplanes, right, the air traffic control. We did the camera. We covered a lot of stuff. Let's see if we can find more. Again, I'm not using examples with numbers, because plugging numbers in here, it's literally, okay, when camera is at 45 degrees, the rocket is doing 11,000 kilometers per hour, right? You can plug those numbers in and compute the change in angle that you need to adjust. So that's not an issue. I hope that's not an issue, to plug the numbers in. Ready? All right. The class ends is like 8:50, 8:20. What time? Lies. 7:35. I was just testing you all, and you just failed me. So the next problem is another engineering problem. You want to design a system that will cut off the supply of the materials which are dropping on a conical pile. So what do we have? We have some kind of conveyor belt, right? There's a whole structure. So there's a conveyor belt, and sand, gravel, corn, I don't care what, is deployed with this belt. It falls from the belt on a little conical pile, and that pile becomes larger and larger and larger and larger, and when it grows all the way up to the conveyor belt, then the conveyor belt will be filling up only on kind of one-sided until it starts backing up all of this stuff on the belt and break the whole system. And those are very expensive. Now, you have an option to employ someone to stare at it and then push the button when it's right almost up to the conveyor belt. Or you can design automated switch. Now some will say, well, how about you just use a photocell, and then when the photocell, no. Because photocells are not good for these types of environments because you have a lot of dust, right? You're going to get dirty. You can have a bird or a spider or whatever cut off, right, at the thing, so not good. So let's take a look at the formula again, right? Because when you are able to set up the formula for situation like this, aha, yay, right? You can compute the time at which you need to stop this. Now, what do we have as our variables? Well, it should be clear that the radius r is progressing in time, right? It's growing. And also the height h of the cone is also growing in time. And we also have the amount of stuff coming in, and that's clearly dV dt, because it's coming in at the rate. I can set up my conveyor belt to bring in, I don't know, 3 cornflakes per hour, right? Or 3,000 per second, right? That's just amount of stuff. What this means in this setup here is just the amount of stuff coming in. That's all it is. Amount of stuff going on a pile. Now, that clearly, right, because you have the volume coming in, it changes the volume of the whole thing. So it better be the volume formula that connects all of this. And it does, right? So, what's the volume for a cone? Exactly. It's clearly V equals 1/3 pi r squared h. I mean, that's obvious. It's not obvious? No. Yeah, because I didn't have my little talk on the formulas. That's why it's not obvious. So we'll deal with that right after this example. So now I have my volume formula, and we know what we do with these things. We hit them with the time derivative, because we want to see the way this evolves in time. Great. The left-hand side, dV dt. The right-hand side, you have pi over 3 as a constant. And now what do you have with r squared times h? Say the words. Product rule. R is a variable because it's changing in time. Height is the variable because it's changing in time. So they're both variables, therefore it's a variable times a variable, and that's a product rule. Yeah. So, let's go. Copy the first one, r squared, the derivative of age, DHDT, plus copy the second, which is age, times the derivative of r squared, which is 2r dr dt. Now that's a little mess over there, right? We can try and make it prettier, but you know, in some cases it just can't be done, no matter the amounts of stuff. So dV dt is pi over 3, and now I have r squared dh dt plus 2rh dr dt. That's your formula. This is the related rates. What are the rates that are related? The amount of stuff coming in, which is the volume. The change in height of the conical pile, and the change of the radius at the bottom of the conical pile. And they all change at the same time. Now the cool thing is that one depends on the other. So we can actually reduce amount of variables if we use similar triangles and we have a measurement of the conical pile. So if I am able to measure at a time, right, that let's say height is equal to 10 when radius is equal to 3, because that will create a 6 in diameter. Actually, no, let's use 6, so it's 12. All right, 6. If I have this, right, then I can come up with a similar triangles situation where, since it's getting larger, right, this is the height of 10 and this is the height and this is the radius of 6, over time you can write the proportion where you say what 10 is to height, 6 is to radius. And you can solve this either for height or radius. So cross multiply, you have 6h equals 10r. And from there, height h is 10r over 6. And the height is 5r over 3. This is relationship that is already reducing your variables down. So you have to make the measurement of some kind at one point in time to say, okay, the pile is 10 feet tall and 3 in radius, which is 6 in radius, which is 12 across. Now, as soon as you make that measurement, we come up with this type of formula which already eliminates one of the variables. In this case, it eliminates age. But we can also take the time derivative of it and eliminate even the rate. So DHDT is equal to 5/3 DRDT. And now this and this plug in to the related rates formula. And you immediately eliminate a lot of variables. So now dVdt is pi over 3, and now I am replacing every h. So I have my r squared, and instead of dH/dt, I have 5/3 dr dt. Plus, now I have 2rh. Okay, 2r, and instead of h, I have 5r over 3. And then I have dr dt. Yeah, good. Now this compresses the formula greatly. I have pi over 3, 5/3 r squared dr dt, plus 10/3 r squared dr dt, and you see they have the same variable part, so these are like terms you can add. So that's 15/3, and that's 5. So pi over 3 times 5r squared dr dt. Just use basic parentheses. And that is, at the end, 5 pi over 3 r squared dr dt. And there's your new related rates that has less variables. And I will obviously encourage you, when you go home, instead of, right, as you are reviewing this problem, instead of solving it for age, solve it for r, and then plug and get the alternate form, right, where you get to eliminate the other variable. So now the entire problem is only in terms of r and the change in radius. Now that's something that you can measure. Radius, you can always stretch the tape, and then the change in radius you measure as well, right? Right? How much did it grow? How much did it grow? Grew in certain amount of time. But you can also see this one you can measure as well, because you know how much stuff is coming in on a belt. So all of these things are good. Ready to learn all volume formulas ever? Anyone? Thank you, both of you. Out of 10,000 students in this classroom, 2. All right. Well, they don't know. I'm going to break this into 3 categories over here. So the first category here are prisms and cylinders. So we have a cylinder like this, or we can have a prism. And all of these volumes for the shapes that look like this is volume is equal to base times the height. And this is area of the base. So that's the formula. So clearly for the first one is the cylinder. The area of the base, right, the area of the circle is pi r squared. So pi r squared times h, and that's the formula for it. So you're not learning every shape separately. You are learning that as long as you can figure out the area of the base, in this case it's either a square or a rectangle, say times b, times the height is going to give you. So area of the base times the height for all objects that look like that. Now you can have a pentagon, you can have a triangle in a base, you can have whatever else, right? As long as you can compute the area of the base times the height, and you have your volume formula. Second category is the ones that I call spiky objects. We're going to have a cone in that category. But you're also going to have the pyramids and things like that. So everything that has a spike on top. All right. And these things have the volume of 1/3 base times height. So if it's spiky, right, it has that. And now the third category, the last one, has only one object in it. And that is sphere. It's a perfect object. Sphere, also known as a ball, with its volume of 4/3 pi r cubed. Guys, this is what you're memorizing. This is what you're memorizing. The shape with associated formula, and then just figure out the area. You have the spiky and non-spiky. Spiky ones are 1/3 of these. So what was the cone? I had the cone in our previous problem. The cone formula was 1/3. The area of the base was pi r squared times the height of the cone. So go back in your notes and look at the formula. I use this. I don't keep these formulas each, separate shape memorized. When you have the pyramid, right? It can have a square base. It can have a triangular base. You can have a 8-side base, whatever it is, right? As long as you can compute the area of the base times the height times 1/3, because it's spike, it's pyramid, you get the volume of that shape. Next problem. You know how much you love word problems. There's another word problem that is going to bring you back to your childhood. Yes. A house with a chimney and the window and the door, and a person outside with a scarf and a hat, maybe skis, I don't know, whatever. Thinking I'm gonna go up, right? Definitely a non-friend right here. The little snowball, also scarf, right? It's cold. Tosses a little snowball right here, which starts rolling. Well, we all know what happens. Seen these on the TV? Of course you have, right? Great. So the myth is that you put a little snowball on top, it rolls, picks up the snow, becomes larger and larger and larger and larger, right? Let's compute some rates of change. So how fast is the volume changing as this rolls down the hill when radius is so and so? Great. So how fast is the volume changing? When radius is equal to, I don't know, 3 feet? Too much. Let's go with 1. And change in radius is, I don't know, 0.7. Let's go 0.07 feet per second. Whatever. Great. Volume for the ball, you have to memorize 4/3 pi r cubed. Then we are going to take that volume, 4/3 pi r cubed, and hit that with a time derivative to find related rates. The time derivative of v is 1, followed by dv dt. On the other side, I have 4 pi over 3 copy, and then the derivative of r cubed is 3r squared. Again, dr dt following with the chain. We must. 3 is cancelled, and we have dv dt is equal to 4 pi r squared dr dt. Related rates. Now, I gave you that the radius is 1. So dv dt is equal to 4 pi, radius is 1 squared, and this is 0.07. So the whole thing is 0.28 pi. Feet cubed per second. Now you can go and compute if you really care. Right? Times pi. But I don't think anyone does. So units are a point on your exam in the answer. So you need to make sure that you understand dimensional analysis. Length is just meters or just inches or just feet. Area, meters squared, feet squared, inches squared. Volume, cubed, inches cubed, meters cubed, right, and so on. Divide them by time to figure out the rates in time. And so on. If you really want to challenge yourself, try problem 19. You will look at problem 29. Draining a tank, it's a conical problem. And so on. So there are a lot of cool problems, like 60 or something problems. Problem 46, very relevant to your project coming up. And if you have nothing to do next few days, problem 52. Problem 52 is really nice. It took me some time to figure it out. Look at that. So you're watching the Ferris wheel go around. So you're observing this point going around. So an observer stands 20 feet from the bottom of the 10-meter tall Ferris wheel, and the line is perpendicular to the face of the Ferris wheel. The wheel revolves at the rate pi radians per minute. You observe the line. Simply said, let's read this thing. Now, obviously, this is the grandmaster stuff. Okay? That means you did all of the other problems in the book, and this is the final boss. Right? You win that one, nothing to worry about. There was another, this one, viewing angle. I did this at my theater, right? Perfect. Except I did not just for the screen, I also did for the sound, and that one has more variables. So you put 8.1 around. So those are the things that you can consider. So those are the boss problems as you guys planning on getting these things, practicing these things. Good. Questions, concerns? Nothing? All right, then we're going to the next thing. We'll just say bye over here. Bye.